Alright, today we're going to look at a problem that reads, a force of 30 newtons is required to maintain a spring stretched from its natural length of 12 centimeters to a length of 15 centimeters. How much work is done in stretching the spring from 12 centimeters to 20 centimeters? Well, the first part's talking about a natural length of a spring. So from the starting point of the spring to this box is called equilibrium because the box is not moving. It is sitting at rest and it's not being pulled in either direction with any kind of force. Well, once we apply a force going to the right, you're able to stretch this spring. And that requires 30 newtons of force. And when you do this, you're taking it from the resting place of 12 centimeters to a final place of 15 centimeters. Your displacement being this 3 centimeter difference between the 15 and the 12. Well, what the question is asking is, how much work do you have to do to stretch it from 12 to 20 centimeters? We don't know what the force is, but they want to know the amount of work. Well, you can't find the work without finding the force. So let's explain what force is. Force is the spring constant times the displacement. The spring constant is that constant pull of a spring line to close back together like this. So, to find the work, we need to find the force. Well, we can't find the force without K. But if we go back to drawing number 2, they give us the force and they give us the displacement. So using those, we can solve for K. Well, for all your units to work out properly, you need to convert centimeters to meters, which I did here. So we know the force being applied is 30 newtons. We don't know K, so we're just going to use that as our variable. And we're going to multiply it by the displacement, which we said was 3 centimeters, or 0.03 meters. So plug this in, solve for K, and you get 1,000 newtons per meter. So now you can take this K and come all the way back up here, and you go back to your work formula. Well, we now know what K is, and we're changing the displacement on this last problem from 0.03 meters to 0.08 meters. Reason being, we're stretching it from 12 to 20 rather than 12 to 15 centimeters. So when we plug this in, we're going to have work equals the integral from our lower bound, which is 0.12 meters, to our upper bound of 0.20 meters. And it's going to be K times our displacement. So it's 1,000 newtons per meter times the displacement of 0.08 meters dx. So when you just multiply the 1,000 times 0.08, we're going to simplify and we're just going to get 80 newtons. So work equals the integral from our lower bound to our upper bound of 80 newtons dx. Well, when we integrate this, we get 40x. And we're going to evaluate this from 0.12 meters to 0.20 meters. So you have to subtract your upper bound, or subtract your lower bound from your upper bound. So we get work equals 40 times 0.20 minus 40 times 0.12, which will give you an easy answer of 8 minus 4.8 to get a total amount of work being done on the spring in the box of 3.2 joules.